having to thank the Fab Lab Intern Group for sponsoring our participation. My name is Anna Shvets. I'm a deep learning researcher at Fab Lab in Paris, and together with my collaborator Samra Darkazanli, who is developer at MSA French Informatics Company, we'll present our experience in building a custom convolutional generative adversarial network which generates harmonic sequences given the input chord with its further integration integrative module of our VR application, Hrafs if in Harmony Learning, designed to develop practical auditory skills in recognizing chord structure and functional relations in music sequences. Okay, so recent advances in the field of deep learning neural networks influenced the approaches in computer-aided composition, which nowadays is enriched with a plethora of deep learning architecture, among which we may find such architecture as neural networks, long short-term memory networks, generative adversarial networks, autoencoders, variational autoencoders, and transformers. Among the domains of the application of this architecture, we can find a generation of melody, accompaniment, temporal dependencies, as well as the generation of entire sections of music in a specific musical style. However, despite the variety of solutions, the conditional harmonic sequence generation in a symbolic domain, which we use, still leaves a room for experiments. And in present paper, we propose an adaptation of the conditional GAN architecture issued from the computer vision domain, preserving convolutional layers for computing sequential data. Upon our knowledge, is the first experiment on using conditional GANs for generative music. Okay, so in present VR project, we are aiming to develop harmonic ear and the theoretical understanding of underlying relationships of chords attributed to functional groups via exploitation of the original representation of music knowledge based on the system graphs. So the underlying methodology was proposed in my PhD in computational musicology, and since then I used it with success in building interactive learning activities for students. The understanding of music theory is added with the use of specific color scheme. You can see here, presenting music functions applied to schematic representation of chords inside the system of graphs. The first image shows the tonics of dominant and dominant groups with their own group of colors, which correspond to the normal representation of chords in the system graphs. The squeezed representation of three sequences in a vertical triad, shows the consistency of the two first chords, so the sense degree of the tonic and second version of the dominant, with the variability of three of the third chord, which are the bottoms of the of those graphs in the vertical triad. So finally, the cross between a horizontal and a vertical triad reveals the interconnection in between the elements of the system via the common passing chords. Okay, so the explicit visual representation achieved with possibilities of VR application context and proposed representation methodology helps the learner to focus on a chord phonism and functional relationships between chords, which increases the overall learning efficiency concurrent with the pedagogical experiments conducted previously. Now I will give the word to my collaborator who will explain how the application works.
Hello, everyone, and thank you for having us. So our application is created using a 3D engine software, Unity 3D. It is built for a VR device, and we recently made it compatible with the newest Oculus Quest device, the second edition of the Oculus Quest. Unity 3D has a personal free plan, among other plans, so it's quite practical to develop a VR app with Unity. And for the Oculus device, it is quite easy to use all the Oculus assets and libraries. Our app is not on the store yet, but we need to work more in order to make it compatible with the store requirements. But we plan to deploy it on the App Lab as soon as our first version is fully operational. Let's walk through the app. Our app has three main parts or modules. First, we have an explanation module. It takes form of a big virtual room, like a temple, like temple of knowledge. In this room, the explanations and the basic theories are on the walls, and the user can navigate through them from a wall to another. And the learner needs all these basic knowledges in order to be able to, in order to be ready for what's next. Next, a main room called the study room. It exposes all the study material. Here the learner can navigate through triads, vertical and horizontal triads. He can listen to sequences. He can use an automatic sequence playing mode, or he can select the chords freely. For example, he can explore a vertical triad, listen to all the sequences in the vertical triad, or select chords of his own. Besides listening and learning the sequences, the user can check his knowledge with an auditory recognition sequence. Finally, a creative module called the practice mode is a new feature. In this mode, we use a computer-aided sequence generation. And this model is not shown yet, but it will be discussed further in detail. Here's a quick video demonstrating the usage of the app. It is actually recorded from the device. Here we are in the first room where we have some information about the app. There's an about button and a start button with some basic information and some information about how to use the app. Next, the learner moves to the temple of knowledge, or the second room. So the explanations are on the walls. He can read them, he can navigate through them, and he can use some hyperlinks in order to check them. After this, the user can go to the next room called the study room. In this room, we have the basic study material. We can see the graph system here in virtual reality. For example, here we'll see the user checking out horizontal triad. And in the same time, he can check the augmented score representation on the right. So the user can do the same thing with a vertical triad and listen to the sequence as well. Here's a vertical triad. Okay, that's all for this part.
Okay. So now, can you hear me? Yeah. So now let's move to the model description, starting with the project conditions. Here is the next slide here. Oops. Yeah, perfect. Here it is. So the iModel architecture choice was conditioned by the context in which the model was used. That is a creative module of the VR.
There's some echo, Anna. I don't know where it's coming from.
I'm sorry?
You have an echo at the moment.
I think if you're going to play a video, you might need to mute your microphone.
Okay, can you hear me all right now?
Now it's okay. Now it's okay.
Now it's okay.
Okay. Earlier there was echo.
Okay, sorry, it was my fault. I thought I needed to activate the ear, but if you hear me okay, it's no problem. Okay, So among the requirements of the project was, the usage of the model in a specific VR room, and that the user needs to interact with the content. So the model should take the input in order to generate the sequence. And as the main restrictions of the project, there was the obligation of generating diatonic harmonic sequences in a CK only, because the content to explore it's in a C major key. And so we couldn't use any other model. We needed to train it, to construct and train it on our own. And also the chosen chord should have conditioned the content of the sequence to generate and to be inputted as a class to the model. So based on these requirements and restrictions, we checked towards the architecture choice, and that was the conditional GAN generation. The conditional GAN. Okay, perfect. So before considering the architecture of the model in detail, let us discuss a dataset and its preparation pipeline. In view of the diatonic content requirement, a classical along romantic music styles were chosen to form a training set of the model using the data present in Kaggle dataset classical music. The distribution of the example per composer as well as the number of extracted chords is shown in the table on the right. The chord extraction itself was made via the Python library for computation musicology, Music 21. After the information extraction from MIDI files, the chord sequences were transposed to CK and transformed to their Roman numeral representation. So after that, we worked with the string object, eliminating any other chord alternation, because we don't have alternation with the application. It's diatonic based, as well as eliminating the sequential chord repetitions, because our sequences needed to be 5 chords max to be displayed to be mapped in the VR content, and the content should not have the repetition. So each individual chord needs to belong to other degree of the scale. So after that, we formed the input features. There are 3 steps. So the array of chords is divided into 7 classes, where the first chord is a representation of the class. So basically, is a degree of scale, 4 seconds, fourths, etc. The chords of each sequence are replaced with their indices from the dictionary of unique chords. And then the chords are converted to tensors and normalized between -1 and 1. Okay, so before considering our example of conditional GAN, let's take a look of the basic GAN architecture. So the principle of the work of GAN architecture is the competition between discriminator and the generator. So a generator receives a noise, it generates a sample and gives the discriminator to define whether it's real or fake. And discriminator has the access to the real world images or examples. In our case, it were the sequences. And it has those 2 inputs, so real examples and fake examples. And he needs to define what is real, what is fake, and give his assessment with the loss function. Then the result of this loss function is put backwards to generator, and in such a way, generator learns how it should ameliorate the content in order to be more resembling to the real examples. Okay, so now let's move to our conditional GAN architecture. The network was built in the PyTorch deep learning framework. The generator is composed of triple stack of transposed 1D convolution, batch normalization, and rectified linear unit. And the transposed convolution basically means the reverse operation of the convolution. So if in a convolution we are diminishing the information, extracting the feature, here we are expanding it. and with the final stack of transpose convolution and tangent layers. The discriminator was much like the generator, but instead of 3 blocks, it had only 2. It had the convolutions as the layer, not the transpose convolution, and the leaky rectified linear union optimization function. Leaky because we want to share the sum of the weights with the generator in order to the generator to better converge, and the final layer, which was just a convolutional layer. Okay. Now, while the training, here we have the visualization of the loss function during the training. So the extracted chords that we prepared via our pipeline, they form the input features to our network, and this data was passed to the generator and discriminator for 100 epochs. And the learning curves of the generator and discriminator shown here. Here's discriminator and generator, shows a good dynamic of the loss decrease for both parts of the network. So we're decreasing in our loss values. The noisy shape of the curves is rather expected for GAN architecture, and in the end of the training process, 2 models were rather balanced, which is the goal of the GAN, with the generator loss equal to 0.74 and discriminator loss to 0.67, so almost 7, which is a good metrics for GAN. Okay, I'm passing the word to my collaborator, who will explain in details the model integration into the VR app. It's time for you, Sam.
So after the training process is finished, the best checkpoint of the model is saved into a binary file. Then this file is integrated into a web application using a Flask framework. This particular Flask framework allows us to use Python code and libraries. So this way we can use our AI model and deploy it on the cloud. And in our case, it's on a Heroku server. For example, when the user needs to generate a sequence, he selects the first chord, and the VR application sends that chord in a JSON format to the AI on the cloud. The model does the prediction, and the predicted sequence is returned to the VR application in JSON format as well. Then the VR app displays and plays the sequence. Here's a demo of how this plays to the user. So we are on the graph system. The user will select a vertical triad on which he would like to work. Then he will select a first chord. And the app displays the predicted sequence. So he generated a sequence.
Yes, perfect. So this is our new feature, and here we come to our conclusions. Summarizing, in this paper, we have shown an adaptation of the convolution GAN architecture to sequential data, representing harmonic sequences of diatonic chords. We also demonstrated how this type of architecture, along with the generated content, serves a specific use case, which is the integration to the creative module for computer-aided sequence generation in a VR harmony learning application. The axis of the future work will include the improvement of the network stability, since our network is still prone to mode collapse. It's generating, it likes to generate some types of sequences over other. We'd like also to ameliorate the data filtering process. So instead of a simple deletion of repetition and the alternation, we plan to apply more sophisticated sophisticated process in order to generate better training data. And we'd always like to augment the number of classes to include chord inversions into the generation condition, which might be useful for the learner of the app. So that's it. Thank you for your attention. And if you want the very first version of the very first production version of the app, just drop on us an email, and we'll be happy to send you when it's available on the Unity Lab. Thank you.
Right. Thank you very much, Anna.